Hi again everyone, I'm Chris Tisdell and I'm a mathematician at the University of New South Wales in Sydney, Australia. And in this presentation I'm going to share with you some forthcoming mathematical research of mine. Now in particular the ideas are going to be published in the Journal of Difference Equations and Applications, and this video can be thought of as a slightly more detailed presentation of the research note that will appear in the future in that journal. Now that particular note is only 4 pages, so the material is quite dense. This video kind of complements the future research note quite nicely, I believe, because I have a little bit more time to expand on ideas and keep things a little bit more self-contained. Now, even though the ideas in this presentation are new research, I'm very confident that a good undergraduate student who knows what a metric space is could follow along with most of this presentation. The rest of the ideas can be sort of woven into this presentation to keep it somewhat self-contained. Now, if you want the detailed background for this presentation, you can find them in other videos where I've posted what is a metric space, what is a complete metric space, and so on. Now the title of my research is called Improved Contraction Methods for Discrete Boundary Value Problems. And in particular, we're going to look at a boundary value problem, or BVP, involving a first order difference equation, which we're going to call the discrete BVP. And the question is, when does that problem admit a unique solution? Well, I'm going to present some sufficient conditions under which the problem under consideration will have a unique solution. And the innovation in the ideas involves a strategic choice of metric or distance function and combining it with a classical inequality known as Hölder's inequality. And what this means is that you can apply a famous fixed point theorem of Stefan Banach to these kinds of problems, where before, well, actually, you couldn't apply this famous fixed point theorem of Banach. So in that sense, the ideas that I'm going to show you today improve the current results in the literature by enabling this special theorem of Stefan Banach involving contractive maps to apply to a wider class of problems. And I'll show you some examples at the end, where my results apply, but existing results in the literature don't apply. Okay, so let's have a look at the boundary value problem under consideration, the discrete BVP. Okay, well here in 1.1 I've got a first order, possibly non-linear difference equation. The delta x sub I is just the forward difference. H is the step size and f is some potentially non-linear function. So we take an interval 0 to big N and we slice it up to form our grid points. The mesh size, if you like, is H, and each of these points is labelled T sub 1, T sub 2, etc. up to T sub I. Now, in general, T sub I is just IH for I equals 0, 1, 2, 3, etc., all the way up to little n. Now you'll see that we've taken this difference equation and coupled it with some boundary conditions. Okay, so together these things are called a discrete boundary value problem. So here u, v and w are just constants, and you can see over here we make the assumption that, or make the condition that u plus v is non-zero. So these types of conditions are known as non-periodic boundary conditions. Okay, now this kind of problem, which you may have not seen before, You can think of it as a analogue of the following first order boundary value problem for ODEs, or ordinary differential equations. Here the prime is just ddt, so this might look a little bit more familiar to you than this problem. Okay, well, next question is, why would you want to study this discrete BVP? Why is it interesting, and what are the applications? Well, I can think of two main reasons. Firstly, sometimes in discrete phenomena, discrete equations, discrete boundary value problems actually give a better approximation or a better modelling or description than a problem like this. Okay, and secondly, these kinds of discrete boundary value problems often arise when you want to approximate the solutions to ODEs and the associated boundary value problems. So in my experience, there's two kinds of motivation for studying a problem like this. One is discrete modelling, and the second is numerical significance and connections with solutions to the corresponding ODE and boundary value problems. So what we're going to do is present some sufficient conditions under which this discrete boundary value problem has a unique solution. Now the method involves a famous fixed point theorem of Stefan Banach involving contractive maps. Okay, well, just a little bit on the current literature. The boundary value problem 1.1, 1.2, the discrete BVP, has been studied by many authors, and I've listed some here. And they use other methods, for example, lower and upper solution method, a priori bounds and Brauer degree. Also myself and other authors have studied second order discrete boundary value problems. Now the ideas that I'm going to present and share with you today complement the ideas in these papers and appear to be of a slightly more constructive nature, because we're using Banach's fixed point theorem, which not only gives you existence and uniqueness to certain problems, but it gives you a way of approximating the solution or calculating the solution. So it's slightly more constructive than these works here, whereby the real outcome from these papers is just existence, for example. Well, in section 2, I'm going to present the preliminaries, but the main results actually lie in section 3. And the idea is to formulate the discrete BVP as an equivalent summation equation, then define an operator working in complete metric spaces, and the innovation lies in a strategic choice of metric within this metric space and an application of Holder's inequality, and this enables the mappings involved to be contractive under the metric that we choose, whereas sort of traditional approaches you couldn't get a contractive map under traditional approaches. Okay, so that's the real innovation. So what this means is that this classical fixed point theorem of Stefan Banach can actually be applied to a wider class, a wider range of problems where it couldn't before. So that's what the advancement in knowledge that these results provide over existing literature. Okay, and at the end I'll give you an example where our results, or these results, apply, and for example the results in Mohammed et al. Don't apply. Now, by the way, all these references I will show you at the end of the presentation. Now, what do we mean by a solution to the discrete boundary value problem 1.1, 1.2? what do we mean when we say that x is a solution to this? Well, I'm going to use this x tilde to represent this vector in xn, and graphically it might look something like this. Well, you sort of slice up your interval to form your grid points, and the solution might look something like this. So it's a vector in Rn plus 1, and it has elements that satisfy the difference equation, and also at the endpoints the vector satisfies the non-periodic boundary conditions. Okay. In this section we're going to talk about some preliminary results that will make the proof of the main results a little bit more manageable. Suppose f is defined on this set and is real valued, and u plus v is non-zero. Then in the discrete boundary value problem, 1.1, 1.2, and the following summation equation are equivalent, with this g function defined in the following way. Now, this g function has a special name. It's known as Green's function. For our boundary value problem 1.1, 1.2. Now note that g is just defined, u and v are all constants here. So note that g is defined kind of in a piecewise constant way here. And as a result it's simple and it's pretty easy to work with. So that's reasonably desirable. Now, you might think, why do we want to show some sort of equivalence between this problem and this problem? Well, in the proof of the main result in fixed point approaches, we don't actually treat this problem directly. We convert it to a equivalent summation equation and then work with that. Okay, so this is actually what we're going to work on rather than this. Okay, well, I haven't put this result or the proof in the note that's to appear in the JDEA, so I can discuss it in a little bit more detail now. So, okay, let x tilde be a solution to this problem. What we can do is start with 1.1, move the h up there, and then sum up both sides. Okay, so I get something like this. And on the left-hand side, of course, the fundamental theorem of discrete calculus just gives you the following. Oh, F. Okay, so then that you can just bring it to the other side and you get the following here. Okay, so if we can determine what x sub naught, some expression for x sub naught, then we actually have our summation representation. Okay, so we take this sub in little I equals little n, and we have this. Now, what we can do is use the boundary conditions 1.2 to eliminate x sub n in here. Okay, so using the boundary conditions, you can come up with the following, and then replace. So essentially, you express x naught in terms of known things, your f and these constants. Okay, so essentially just take x naught up there and replace it, and you get this big mess. Now, to clean it up a bit and to give it some nice properties, we can sort of recast it in this equivalent form just by splitting this sum up. So sum from j equals 1 to I minus 1, and then sort of combine two sums into one. And you can come up with your summation representation 2.1. Okay, well that's proving it one way. If we let x tilde be a solution to this, then all we have to do basically is show that x tilde satisfies this and this. So basically take the difference of both sides and show that you get this, and then test the boundary conditions. So I haven't actually put that part in, but it's reasonably straightforward. Okay, so this is going to be a big part for us in the proof of the main result. Okay, so the following two lemmata or lemmas will be used again in the proof of the main result. Suppose Q is positive and let big G be the Green's function defined in 2.2. Then we have the following. Whoops. Okay, essentially this is equal to this. Now, I haven't proved it. This is actually reasonably easy to prove this because G is a pretty simple function. It's a piecewise constant function. So you can take these sort of things outside the front of the summation. So that's reasonably easy to prove. So I won't do that. And the other result that we'll use is Hölder's inequality. Now, if you want to see a proof of this, then you can have a look at my YouTube video on that, which is in the references at the end. So suppose P and Q are both strictly greater than 1 and they satisfy this equation here. Then for all vectors in, say, r to the n plus 1, we have this inequality holding. And we'll use that a little bit later in the proof of our main result. Okay, well, our analysis of the boundary value problem will be set in the environment of what's known as a complete metric space. So if you want more details on a complete metric space, please see my video on YouTube about that. Essentially, a metric space is a set coupled with a way of measuring distance between two elements in that set. And a complete metric space is a special kind of metric space whereby special sequences called Cauchy sequences always converge to an element of the set big X. So we're going to form the following complete metric space. We're going to consider the set big X to be r to the n plus 1, and we're going to couple that set with a way of measuring distance between vectors in r to the n plus 1. The distance function or metric is defined in the following way. Now, P is just any any number that's greater than or equal to 1 here. Okay, now, it turns out that this set coupled with this metric or distance function is a complete metric space. Okay, and again, I've proved that in this video. Okay, now with respect to Banach's fixed point theorem, which is what we're going to rely on in the proof of our main result, we need a little bit of terminology for that. So let big X comma D be a complete metric space, and let F be some map that maps big X back into itself. We say the mapping is contractive if there exists a constant alpha strictly between 0 and 1, such that for all pairs of points, little x and little y in our set big X, the distance from f of x to f of y is less than or equal to alpha times the distance from little x to little y. Okay, the constant alpha is called the contraction constant of f. Okay, well let's have a look at Banach's fixed point theorem. We're ready to start that now and have a look at that. So this is a very famous fixed point theorem due to Stefan Banach in 1922. So suppose we have a pair, a set big X and a distance function or metric little d, which is a complete metric space. And suppose F maps the set big X back into itself and is a contractive map. So this holds for some alpha between 0 and 1. Then F has what's known as a unique fixed point in big X. That is, there exists a unique element, u, in our set big X, such that F of u equals u. And if we define a sequence, Fi of u, by starting at some arbitrary point or element in big X, and then having F operate on that point, so F1 of y is just F of y, F squared of y would be F of y, okay, and so on. Then the sequence converges to the unique fixed point for each starting value in our big X. Now furthermore, and I'm not going to discuss this thing too much in this particular presentation, mine's more about the existence and uniqueness, but under the conditions of this Banach's fixed point theorem, if we start at some arbitrary element, y in big X, then Banach's theorem provides an estimate on the error between the ith iteration Fi of y and the fixed point, namely this thing here. Notice this is in terms of the contraction constant. Well, Banach's theorem does quite a few things. It gives you the existence of a unique fixed point, and it gives you a theoretical way of computing or approximating that fixed point through this iterative scheme. Okay, so on to the main results. The main result is as follows. Let F be continuous and the coefficients in our boundary conditions satisfy u plus v is not equal to 0. If there exist constants L, delta, P and Q satisfying these conditions such that the following three conditions are satisfied, then our discrete boundary value problem 1.1, 1.2 has a unique solution for each h between 0 and this delta. So let me sort of deconstruct this a little bit to show you where these each condition comes from and what it's needed for. 3.1 is known as a Lipschitz condition on F. Now, that's a very famous condition, and I have a video in the references talking about Lipschitz conditions and when F satisfies Lipschitz conditions and things of that nature. 3.2 is related to the contraction constant, alpha. Now it turns out that this big mess on the left-hand side is actually going to be the alpha in Banach's theorem. So you can see here, we want to show that big F is contractive, so we want to show an alpha exists between 0 and 1 such that this is satisfied. Well, this is actually going to be the alpha. Okay, and finally 3.3 is just related back to Holder's inequality. Okay, we needed this condition on our P and Q to invoke Holder's inequality. Okay, so let me talk about the proof now of this main result. The idea is to use Banach's fixed point theorem. Okay, so the first thing we need to do is set up a complete metric space. So here's our set, and here's our way of measuring distance between two vectors in Rn plus 1. Now, this kind of general metric here is credited to Minkowski. Okay, now the pair big X d sub p, where big X is this, is a complete metric space, and the proof is in this video here, which you can look up on YouTube. Now what we do is we take our, the next thing we want to do is form some sort of operator that maps the set big X back into itself. Okay, so what we're going to do is rely on lemma 2.1, which says that the boundary value problem, the discrete boundary value problem, 1.1, 1.2, is equivalent to this summation equation where g is the Green's function here. Okay. Now, based on this right-hand side of the equivalent summation equation, we are going to define an operator big T tilde. I probably should have written big F here or something, but I'm just going to write big T tilde. That's essentially this right-hand side. Okay, so what you can see hopefully now is that if this has a fixed point, if T tilde X tilde equals X, then this is the same as that. So if we can show that there is an X tilde that satisfies this, then that's equivalent to that problem, which is equivalent to our original discrete BVP. So that's got to have a solution. Okay. So what our focus now changes a little bit to this, and showing that this has a so-called fixed point. So T tilde X tilde equals X tilde for some unique vector X tilde. Okay, so how do we show that this has a unique fixed point? Well, we want to use Banach's fixed point theorem. Okay, well, we've got our complete metric space. We want to show that our operator maps, in this case, big r to the n plus 1 into r to the n plus 1, and we also want to show that it's contractive. So this is actually pretty easy to show. Okay, the slightly more difficult thing is to show that we have a contractive map on our hands. Okay, so we want to show that there is a contraction constant alpha between 0 and 1 such that this is true for all vectors, pairs of vectors in r to the n plus 1. Okay, so what we want to do is sort of set this up and try to show the contraction. Okay, now working from here, let x tilde and y tilde be two vectors. Consider the following absolute difference. We can come up with this. Now, from here to here, we've used assumption 3.1, which is just the Lipschitz condition on F in our main theorem. Where is it? Okay, this one here. Okay, so we come up with the following inequality. And then what we can do now is, you notice I've got a sum here of two expressions multiplied together. I can apply Hölder's inequality to this sum here. So essentially this right-hand side can be made less than or equal to this for some p and q strictly greater than 1, which satisfy this. Okay. Okay, well, notice here that this is almost the d sub p of x bar y bar. In fact, if I had another little sum here, it would be, it's actually less than or equal to x tilde y, the d sub p x tilde y tilde. Okay, so what I've got now is this right-hand side is in terms of this metric d sub p, and I'm going to try to express the left-hand side in terms of d sub p of this. Okay, well, I can simplify what's in this big bracket just by the earlier lemma in section 2 to get the following. So I can just replace this with all of this. And then, again, I'm trying to form this on the left-hand side. So I can take it to the power p and then sum up and take the whole thing to the power 1 on p. So here I've got d sub p of this, comma this, so it's just this. So using my earlier inequality, I come up with the following. And if h is but less than or equal to this delta, as in the theorem, then I've actually got a contractive map where this is strictly less than 1. Remember, this is one of the conditions of our theorem, 3.2. Okay? So, we've shown that our operator t tilde maps r to the n plus 1 into itself. I've got a complete metric space when I couple this set with this metric, and this working shows that our mapping t tilde is contractive. So all of the conditions of Banach's fixed point theorem are satisfied. So what it means is that our mapping t tilde has a unique fixed point, and this yields the existence of a unique solution to our summation equation, which is equivalent to showing that there is a unique solution to our discrete boundary value problem, 1.1, 1.2. Okay, and I haven't done it here, but you can go a little bit further and show that you know, this sequence converges to the unique fixed point, and you have this error on the ith iteration, between the ith iteration and the unique fixed point. So that's the main result. So that's it's a reasonably abstract result, and it looks very general. What I'm going to do now is just choose some particular values of p and q that satisfy this and this, and show you how 3.3, 3.2 simplify a little bit. So the following is a corollary. So the main result, just by choosing p and q equal 2, and sort of repeating the argument in the proof, gives you the following. Suppose f is continuous, and again these coefficients add to be some non-zero value. If there exists an L such that f satisfies this Lipschitz condition, that's the same from the previous. And there's some delta between 0 and n such that this is satisfied. Then 1.1, 1.2 has a unique solution for all h between 0 and delta. So you can see this is slightly simpler to this setup. Here p and q are both equal to 2, so this is obviously satisfied, so I don't need that in my corollary. And this reduces down to this when p and q are equal to 0. So I'm not going to discuss the proof too much here. I've just listed the main points. Essentially, you just show that, again, we have a contractive mapping on our hands, and it turns out that this is your contraction constant. This condition ensures that the alpha is strictly less than 1. Okay. Now let me show you an example of the power of these results. And in particular, I've just formulated an example showing the power of corollary 3.2. Essentially, the choice of metric in the proof of theorem 3.1 or corollary 3.2 ensures that a larger range of L's are admissible than, for example, another kind of metric. So here we have the max metric defined in the following way. You look at the difference, the absolute value of the difference of each corresponding component of your vectors, and then you take the maximum. Just consider P equals Q equals 2, and then rerun the proof of, say, theorem 3.1 or corollary 3.2 with this particular metric. Then instead of, say, this condition, you would get this condition. Now this is a stronger condition than, for example, this one here. Okay. Now let me give you an example of a discrete boundary value problem that satisfies, say, the conditions of corollary 3.2, but doesn't satisfy this condition here. I guess it shows that my results are a little bit more wide-ranging than Mohammed's. Okay, so let's just consider the following discrete boundary value problem. And this is a special case of our original result with f defined in the following way and our coefficients in our boundary conditions here and here, and big N equals 1. Now, you can show that this f does satisfy a Lipschitz condition with big L equals 8.5. Remember, the Lipschitz condition is just this condition here. And in this video, if you watch this video, you'll see why, essentially because df dy is bounded by 8 on 5 and df dy is continuous. Okay, but for more details you can see this video here. You can show that the conditions of, say, corollary 3.2 are all satisfied for h between 0 and 1/4. Now, it's interesting to note that this condition does not hold, because if you calculate this with big L equals 8/5, big N equals 1, and U and V given here, you'll get 16 on 5ths, which is not less than 1. So Mohammed et al.'s work doesn't apply to this example, but you can see that, or it can be verified, that the ideas in this presentation do apply. Okay, so that's one of the advances that this presentation makes over existing literature. Now here are some references and further reading. Like I said at the beginning, the ideas in this paper are forthcoming research to be published in the Journal of Difference Equations and Applications. And I'll put a link to the journal webpage when this article becomes available. I'll put that in the description section. Now I'd like to thank Professor Jerry Lattice and all the staff at the Journal of Difference Equations and Applications for their encouragement for me to put this presentation together and research through YouTube. Here are the references, many of which I've referred to in this presentation. Now there might be a couple here where I actually haven't referred to them. If so, then you can just take those as more further reading. So I'll show these to you just very briefly. So I hope this presentation has been interesting and engaging. I hope you find it useful. Please watch out for more research being shared on YouTube in the future.